Welcome back to another video. Today we will take a look at this theorem, theorem 2.4.1, which is a theorem of the greatest common divisor of a and b. So we let a and b to be an integer such that a or b are not 0. And then there exists x and y such that the greatest common divisor equal ax plus by. Okay, for example, you might have GCD or greatest common divisor of okay, let me think, 2 and 10. The greatest common divisor is 2. This number 2 can be written as the form in terms of 2 and 10 with multiplication with integer multiplying them. So number 2 can be written as 2 times 1 plus 10 times 0. Okay, this is one of the example. Another example is okay, let me think of this. Give me a couple minutes. Let's say 6 and 20. Okay, what is the greatest common divisor? Let's use 24. The greatest common divisor is 6. So 6 can be written as what? As 6 times 5 plus 24 times minus 1, because this one is turns out to be 30 minus 24, which is 6. Okay, so if you have a GCD or greatest common divisor over two numbers, it can be written in this form, ax plus by, where x and y are integers. So let's prove this. So we let a and b be integers such that a is not 0 or b not equal to 0. Now we want to show that if we want to show that there exists x and y such that the greatest common divisor is ax plus by. So we have to create a set. Let's build this set. So we let set x to be a set of integer in this form. Let's say you have am plus bn, where m and n are integer. Okay, and we know that the greatest common divisor is a positive integer. So we have to write the condition for this such that this integer is positive. So we gotta have am plus bn greater than 0. Okay, so that's what we have right now. This is the set x. Now what can we do? So the next thing that we have to do is to show that the greatest common divisor can be written as this form, which is the greatest common divisor of a, b. So to pick an element from this set, we need to show that this set is not empty set and try to show that this set is a subset of a set of natural number. Okay, I think you may guess that I'm going to use the well ordering principle. So as we can see, a is not 0 or b is not 0. Okay, when a and b are not 0, it's obvious that we can find integer x and y such that so there exist x and y, sorry for my handwriting, integers x and y such that I should use m and n. Okay, I should use m and n. Let's say m and n. So we're gonna have am plus bn greater than 0, right? Okay, so if a and b are both positive, you have to you can find positive integer m and n such that mn plus bn is greater than 0. If one of them are positive, a negative is negative, let's say a is negative, b is positive, so you can find negative integer m multiplying a and plus bn greater than 0. Okay, so it's obvious that when you have any two integers that satisfy this condition, so we can have that set x is not empty set, because when you have any two integers a, b satisfying this condition, you can find integers m and m such that am plus bn greater than 0, which satisfying this set. So this set is not empty set for any condition. And so what happened? This integer is positive. That means that the set x is a subset of a set of natural number. Okay, what next? When we have these two conditions, we can use the well ordering principle. By the well ordering principle, what do we have? So there exists d in set x such that d is less than or equal to s for every s in set x. So what does it mean by this? D is in set x, right? This set, that means that there exists x, small x and small y. There exists integers x and y such that d equal what? Ax plus by. And this d is the smallest one, is the smallest element in set x. Okay, this is what we have right now. Okay, we can pick up element d from this set x, and d is the smallest one. The next thing that I'm going to do is to show that the greatest common divisor of a and b equal this guy right here, ax plus by. So we have to show that d equal to the greatest common divisor of a and b. So two things that we have to do from this part. The first thing is to show that d divide a and d divide b. Number two, if we let a divide if we let c divides a and c divides b, then you have to show that c is less than or equal to d. Okay, let's prove the first part right here. So we start with this claim. So we have to claim that d divide a. Okay, let's try to prove this. Try to show that d divide a. So we have to consider these two integers, and we have to use the division algorithm. So since d and a are integer and d is in this form, d equal to ax plus y, okay, which is in this set, the set of x. Then the division algorithm implies that they exist q and r, integers q and r, such that a equal to qd plus r, where r is greater than or is equal to 0, less than absolute d. And then we plug in this d into this term right here. So we gotta have a equal to q. Our d is ax plus b y plus r. Okay, what next? The next thing that I'm trying to do is to try to show that r is 0, because we now have, where is our d? We want to show that d divide a. So the remainder r right here must be 0. So I gotta write this equation so that r is a subject. So we gotta have r equal to a minus, minus what? Minus q ax plus b y. Okay. And then let me rewrite this one here. So I gotta let a to be next to each other. So we gotta have a q x minus b y. So we're gonna have a times 1 q x plus b. I forget to multiply q. So we're gonna have q y right here. So we're gonna have plus b minus q y. Okay. So that's what we have right here. So now we have that r equal to this guy right here. And these are integers. 1 minus qx is integer, minus qy is integer. So now let's focus on this inequality. So since r is greater than or equal to 0, less than absolute d, which is d, what does it mean by this? This means that r can be 0, or r is greater than 0, less than d. Alright? And the next thing that I want to do is to try to show that r is 0. But can we have this inequality? And d is the smallest element in set x. So now, take a look at this one here. So if I gotta say, since r is greater than 0, less than d, and this guy right here r, as we can see, this term right here is integer. This one right here is an integer. That means that our r is in set x. Okay? But what is d? D is the smallest one in set x. And r is less than d, right? So we have a contradiction. So but d is the smallest element in set x. Then what do we have? Hence. So I gotta say, so r greater than 0, less than d is false. Okay? This inequality is false. Why? Because r is less than d, but d and r is in set x. Okay? But d is the smallest element in set x, so this inequality, r less than d, is false. So the only thing that is true is r equal 0. Hence, r equals 0. Okay, r equals 0. So what do we have right here? So we gotta have, go back to here, a equal to qd plus r equal to qd plus 0 equal to qd, and d divide a. Okay, d divide a. All right, so that's what we have right here. Okay, d divide a, and try to show that d divide b. Okay, d divide b. So what do we have here? Let's show it. Let's show that d divide b. So the proof is similar. So we have to start with b and d, which are integer, and d is in set x, and x is a natural number. Okay, but it is also similar. Okay, and then what do we have? Okay, let me write d. So our d is ax plus by, which is in set x. So by the division algorithm, what do we have? So they exist integers q and r such that b equal to dq plus r. Okay, where r is greater than or equal to 0, less than absolute value d. Okay, and we plug in this d into here. So what do we have next? We gotta have b equal to ax plus by times q plus r, where r is greater than or equal to 0, less than absolute value of d, which is d. Okay, so we plug in just d equal to ax plus by into this d, and we write the equation so that r is a subject of this equation. So we're gonna have r equal to b minus ax plus by q. Okay, then what do we have? Okay, what do we have is to rewrite the equation so that b is next to each other. So we gotta have b minus a, okay, a qx minus bqy. Okay, and let a to be next to each other. Sorry, let b to be next to each other. So we're gonna have minus aqx plus b minus bqy. Okay, so r is greater than or equal to 0, less than absolute d. Okay, and then I will factorize a. You're gonna have a times minus qx plus b times 1 minus qy. Okay, great. That's what we have right now. So this is our r. Okay, now let's show that r is 0, which is the remainder. So since we have that r is greater than or equal to 0 and less than d, less than absolute d equal to d, that means that r equals 0 or r greater than 0, less than d. But what happened? Since r is greater than 0, less than d, and our r is this one. So our R is a time minus qx plus b time 1 minus qy. And this term is an integer. This term is also integer, right? Minus qx is an integer. 1 minus qy is an integer. Then what happened to this r? This r is in set x. Okay? Then what do we have? That means that r is in set x. Right? Do not forget the set x. Our set x is here, which is a set of a m plus b n, right? A, b are integers, and m is an integer, b is also integer, and multiplying n, which is an integer. So Rx is in this set. But we know that D, which is the smallest element in set X, what does it mean by this? It means that, but I gotta say a D, which is in set X, is the least element in set X. So what do we have? So we gotta have, so that means that R in set X less than D less than the least element in set X. So we have a contradiction. That means that R greater than 0 less than D is false. Okay, great. That means that the only one that is true is R equal to 0. Okay, that means that B equal to, sorry. Oh, what happened here? That means that our B, where's my B? B equal to Q, dq plus R. dq plus R equal to dq plus 0 equal to dq. D is a factor of B, right? That means that D divide B. So right now we have shown that D divide B and D divide A. So the first part is proven already. Now let's prove the second part. Let's prove the second part. Show that if you let C divide A and C divide B, then C must be less than or equal to B. Okay, let's prove the second part. So we have to show that C divide A and C divide B, then C less than or equal to D. Let's prove this part. Okay, so we gotta assume that, I think we first let C to be integer. So let's see to be positive integer. Okay, and assume that C divide A and C divide B. Okay, so what next? I think the next step is easy. Why? If you remember this theorem, if you have C divide A and C divide B, okay, C divide ax plus by for every integers x and y, right? We use this one, and the terms of D is in this form. Okay, so that means that C divide AS plus BT for every integer S and T. Okay, for every integer S and T. What does it mean by this? This means that C divide ax plus by. Okay, and this guy right here is what? Is D. Okay, this term is D. That means that C divide D. Okay, so this shows that C less than or equal to D. So we have shown that when we let C divide A, C divide B, then C divide D, where D divide both A and C. Okay, so we already proved the second one already. So we have shown that D is a common divisor of A and B. All right. Therefore, D D is a greatest common divisor of A and B. And what happens next? AB equal to D, and D is ax plus by. Okay, that's it. So we have proved this theorem already. So if you have the greatest common divisor of AB, so there exists integers x and y such that ax plus by equal to the greatest common divisor of A and B. Okay, so that's it for this video.